Carolyn Matl from UC Berkeley's Heart Lab. Today I'll be presenting our work on a new soft tactile hand. While the palm of this hand is made of a soft, compliant material, the robot can vary its stiffness via a simple actuation mechanism. In this work, we will show how this technology can be used to measure both the geometry and stiffness of objects, which we believe will be essential for the dexterous robotic manipulation of deformable objects like dough. This soft tactile end-effector that we designed can be categorized as a soft optical tactile sensor, meaning that the tactile interface is made of soft, compliant material, and when the membrane surface makes contact with the environment or an object, its deformations are imaged by an optical sensor, like a depth sensor. There's been a lot of recent interest in developing these types of sensors for robots. For instance, the gel site sensor developed at MIT, which is shown on the left, is quite popular due to its high-resolution contact images. Also, the tack tip from Bristol and the soft bubble from Toyota Research can conform to surrounding geometries due to their high compliance, which means that they can perform things like tumor detection or handle delicate objects. Now, there's one particular gel site paper that is relevant for measuring the hardness of deformable objects. However, they note that the gel site performs best when the hardness of the object is closest to the hardness of the membrane. Our design is able to account for this because we designed a unique sensor that can actually vary its stiffness. So just as background to motivate the design of this hand, the first iteration of our sensor, which was introduced at IROS in 2018, was very much inspired by the original tack tip sensor, except that instead of using a gel-filled membrane, we built a pressurized capsule filled with air. The tactile interface was this soft silicone membrane on top, and to increase the stiffness of the membrane, we would increase the pressure inside the capsule. In tandem with increasing the stiffness of the membrane could also be inflated greater than 2 times its original volume. So not only could this device act as a tactile sensor, but it could also act as an actuator and automatically adjust its stiffness to compensate for slipping. So for instance, to hold up this container that has dynamically changing mass. So in this prior work, we really were studying the sensing and actuation duality. And we found that variable stiffness tactile sensing had a lot of potential in expanding robotic manipulation capabilities. However, one caveat to this prior design was that it was pneumatically actuated. And this obviously added some overhead to the entire system and made it more difficult to controllably vary the stiffness of the membrane. So those challenges motivated our new iteration StRETcH, or soft to resistive elastic tactile hand. As you can see, it's no longer a dome-shaped membrane, and instead it's a flat elastic membrane that can be cast very easily by pouring EcoFlex silicone into a rectangular mold. And we attach this membrane to a parallel jaw gripper using Velcro. So instead of varying stiffness via pneumatic actuation, here as the gripper increases its gripper throw, the membrane's internal strain increases, and subsequently this increases the stiffness of the membrane. And this actuation mechanism makes it a lot more controllable. We use a depth sensor to image the deformations of the membrane when it's in contact with an object. With the assumption that the object is convex, the robot can extract out the portion of the membrane that is in direct contact with the object. We tested contact area estimation for the flat circular faces of different sized cylinders, and for specifically centered axial contacts, StRETcH is capable of achieving sub-millimeter accuracy in estimating the diameter of the circular face of those cylinders. And because StRETcH is so compliant, we were able to use it at its low stiffness regime to reconstruct the geometry of very deformable objects like paper boxes or 2D wire shapes like this circle through touch. Here are example point clouds reconstructed from the StRETcH end-effector, making few points of contact with various rigid to deformable objects. So in addition to estimating contact geometry, we wanted to use StRETcH to also estimate the contact load. Now, the mechanical response of StRETcH is a function of both the internal strain state of the elastic membrane, which is caused by uniaxial stretching as the gripper opens, as well as transverse loading and displacement of the membrane from the object in contact, which depends on the contact geometry and the depth of the indentation. However, to the best of our knowledge, there doesn't exist an explicit model that relates the mechanical response of uniaxially stretched neo-Hookean membranes under contact with elastic objects of varying geometries. And while state-of-the-art methods use numerical simulation to make these types of predictions, we wanted to develop a faster method that could be used in a real-time robotic framework. So to relate all these variables, we borrowed an idea from our prior work to use the model of an elastic solid half space, subject to the same contact conditions, as a template for expressing the membrane's variable stiffness. We fully acknowledge that these are structurally and geometrically dissimilar, but we only consider centered contacts and use this template of the elastic solid half space to seed the model for the membrane. So what does this template look like? Well, we imagine that this equivalent half space has an associated elastic modulus, which we refer to in our paper as the effective modulus. This effective modulus will be used to approximate the mechanical response of the membrane when it is stretched. Fortunately, Hertz contact theory provides us with the relationship between the load force and the indentation depth and geometry of the contact with different shapes like an elastic sphere or a rigid cylinder. Using these models as a template, we optimize over this abstract term of the effective modulus to fit the empirical data. This is an example force depth profile for contacts with a 20 millimeter diameter hemispherical rigid probe. Each curve that you see here corresponds to a different stretch state of the membrane, as well as a specific effective modulus. Higher curves correspond to higher effective moduli due to higher internal strains from stretching. Note that this force depth profile is dependent on the geometry of the contact. From empirical data, we can relate the diameter of the hemispherical probe to the effective modulus and the amount of stretch experienced by the elastic membrane. From this graph, we can extract a relationship between the stretch state of the membrane and the effective modulus for a specific contact geometry. This allows us to predict what the force depth profile may look like given a specific contact. Through our validation experiment, we found that for specifically centered axial hemispherical contacts of varying diameter, StRETcH can estimate the contact load within an error of less than 0.025 newtons, which is 1% of its operating region. Because StRETcH can vary its mechanical response, we can estimate the stiffness of deformable objects as well via active palpation. This graph here shows multiple indentation depth to load force curves that correspond to different stretch states of the membrane, where higher curves correspond to the membrane being stretched more. Ultimately, we want to find the force at which the object finally deforms. If we imagine the object to be an elastic body with 1 degree of freedom, we can divide the estimated load force by the amount of deflection the object experiences to make an estimate of the simple proxy for stiffness in newtons over millimeters. So let's see this in action. We can use this force depth profile to save time and efficiently modulate the stiffness of the membrane such that the load force increases monotonically with each new contact condition. However, instead of starting from the lowest indentation depth every time the membrane is stretched, we can jump up the ladder on this curve graph to the next indentation depth that will result in the closest increased load force. So we filled 4 balloons with different substances: air, water, chia seed pudding, which is a viscous mixture of water and chia seeds, and lastly, dry chia seeds. And the robot measured the stiffness of each balloon 5 times. And even though these are technically proxy values for stiffness, since again we're using a simple 1 degree of freedom model for these balloons, you can see that the values increase with each object as is expected, and the estimated values are sufficient for differentiating between materials within this range. We use this proxy for stiffness in our most recent work to efficiently roll out different doughs. So we chose to use the robot to roll blocks of Play-Doh into balls of dough as a way of demonstrating the range of capabilities StRETcH has to offer. In the beginning of this clip, StRETcH was used to measure the membrane stiffness needed to deform this block of dough. Once the robot measured how much the membrane needed to be stretched, it was commanded to roll the block of dough in circles, tracking the position of the dough in parallel to ensure that the robot maintains contact with the dough. Now, this is difficult to do without tactile sensing, since the robot would need to keep lifting its hand to check the condition of the dough. And you can see how, as the dough is moved about the table, the robot hand is able to maintain contact with the dough. Also, the fact that it's a soft membrane that is soft enough to measure where the dough is, and yet still stiff enough to exert force on the block of dough, is important for completing this task. Now, once the robot thinks the ball is round enough, it'll stop rolling the dough. And you can see how, in the before and after pictures, StRETcH definitely did round out the corners of this block of dough. So now next, StRETcH is used at its lowest stiffness to measure the geometry of the ball and to estimate its diameter. Finally, StRETcH is used at its highest stiffness to press the dough ball into a cookie or a scone shape. We measured the circularity of the dough formations from overhead images of the flattened dough balls, demonstrating that this method was capable of shaping dough by varying the stiffness of StRETcH. So in this work, we designed a variable stiffness soft tactile hand that allows a robot to measure both the contact geometry as well as a proxy for stiffness of deformable solid objects. And it also enables new robotic manipulation capabilities such as dough rolling, shaping, and flattening. There are several avenues of future work to explore, since we view this work really as a stepping stone into new directions for soft robotic manipulation and sensors. For one, this design was simple to make and integrate with a robot hand, but we originally intended it to be the size of a finger. In truth, this larger design was a convenient consequence of quarantine, where with limited access to machine shops, we had to rethink and redesign how to make the device. Second, our characterization experiments are valid for specifically centered axial contacts that are convex, which certainly don't cover the broad swath of deformable objects in the world. However, there's a lot of recent work, both on the tactile image processing and soft material modeling fronts, that I believe could really help improve the effectiveness of this technology. Finally, note that the dough rolling algorithm we used for our demonstration was heuristic, and since it wasn't a particularly sophisticated algorithm, it took a long time, sometimes up to 20 minutes. But humans can do this so quickly, so we knew that there must be a more intelligent way to go about this problem. And that's exactly what we set out to accomplish in our most recent work, where we used model-based reinforcement learning paired with our modified StRETcH end-effector to efficiently roll a ball of dough into logs of varying lengths. My co-authors and I want to thank ICRA for this opportunity, and thank you so much for your interest in our work. Please see our paper for more experimental details, and feel free to reach out if you have any questions. Thank you.